Okay, so it's 10 a.m., so we are going to start today's lecture. It is my great pleasure to introduce our today's speaker, Dr. David Strickler. Dr. David Strickler. Dr. Strickler has more than 3 decades of experience working with thin film technologies, thin film deposition, and so today he's going to tell us about how that technology is used in energy applications. So, without further ado.
All right, thank you. Can you hear me okay? Is my mic on?
How is it in the back? Good. Okay.
Wow, okay.
No? A little bit more? Okay.
All right, well, thank you, Michael, for that introduction, and thank you all for showing up today. My topic today is transparent conductive oxide, or TCO, coatings on glass. I'm sure most of you have some familiarity with glass, but TCO coatings are kind of an important technology, but well hidden from everyday view. And I'll talk about photovoltaics initially, and then we'll talk about some other technologies that use these coatings. So I chose this topic for several reasons. First of all, global importance. Photovoltaics is a key part of our solution to addressing climate change, and it's part of the energy transition that we're going through right now. Regionally and locally, University of Toledo has made contributions in this area. I think the faculty has been making contributions over 4 decades before I got into the business. And of course, there have been a number of Toledo area companies start up as solar companies. And the largest manufacturer of solar cells in the U.S. of photovoltaic panels is First Solar, who does most of their U.S. manufacturing right here. I have, and of course the other reason is I have some experience and some confidence in this issue. So just by way of background, I studied chemistry as an undergraduate, and I went on to get a PhD in physical chemistry. And the group I worked in at that time, we made materials for thin film amorphous silicon solar cells. That seemed pretty interesting to me. But when I graduated, when I finished that degree, there weren't really a lot of jobs in the solar business. So I found out that my PhD advisor consulted for this glass company in Toledo, Ohio. So I thought, all right, I'll interview out there. They were hiring, they were looking to start up a new manufacturing process. I had not aspired to go into industry, but I thought, oh, I'll give it a trial. So after 33 years, I decided the trial period's over. I've had enough. So I moved on to retirement. And while I was at Libby Owens Ford, I was in research and development, primarily working on large area chemical vapor deposition of thin films on glass. And in graduate school, I made materials on 4-inch squares. As you'll see, this was a big scale up to go to glass production. Libby Owens Ford, at the time, we made architectural glass, and the motivation for this coating process was really to make energy efficient windows for arc glazing applications. But I'm not going to focus on the architectural too much. And I worked on a few other interesting projects, anti-reflective coatings, and towards the end of my career, I worked on a project on bird-safe glazing. And I know there's activity at University of Toledo on that, so that was pretty interesting. The coatings that we worked on also have applications in automotive. I'll show an example of that. And then, of course, other technical applications. So I went to work in '89 for Libby Owens Ford. The glass industry started here in 1888 when Edward Drummond Liddy relocated the New England Glass Company to Toledo. 10 years later, Edward Ford started a glass company here. Edward Ford was in the glass business. His father had a glass business in Pittsburgh. But there was a little dispute about the Ford plan for that business after Captain Ford died. So Edward Ford decided to go his own way. And then in 1916, Libby and his chief engineer, Michael Owens, started a new company. So in 1930, those companies merged and formed Libby Owens Ford. So why did Libby come here to make glass? Any ideas? Sounds good? Natural gas. The river. Good transport, right? The one most people miss is gas. Energy. We were going through an energy transition there as well at that time. So Pilkington, or LOS, a very successful company for 50 years. In 1960, there was an article in Time magazine on LOF, which called LOF the bank that makes glass. But when the American auto industry in the 70s started struggling due to an energy crisis, right? Libby Owens Ford, which was a primary glass manufacturer for the automotive industry, struggled as well. So Pilkington acquired majority holding in Libby Owens Ford in '82. Pilkington had been founded in 1826 in northwest England. They became a global glass powerhouse by developing the float glass process, which I'll show you in a minute, and then licensing that all over the world. They licensed it to LOF's competitors, they licensed it in Japan, they licensed it all over. And then in 2006, NSG Nippon Sheet Glass acquired Pilkington. NSG had been founded in 1918 as the American-Japan Sheet Glass Company in Tokyo, financed by a Tokyo bank, and they started because they licensed the coal burn process for sheet glass from Libby Owens Glass. In 1931, that company changed their name to Nippon Sheet Glass. So you can kind of see a circularity here, and that these companies have had long interactions even before we were all one business. So NSG Group today, the two major markets are architectural glass on the left. Then there are a couple buildings in China. That's a product called Eclipse Advantage. That product was developed here in Toledo at the R&D center here. It's manufactured in our plant in North Carolina. It's sold all over the world. On the right, you can see two vehicles. The top one, I just put in there to show all the varieties of glass that go into a vehicle. The bottom one is a Tesla. And some people find those cars pretty exciting. I do, because it has an all-glass roof. And the key thing about the all-glass roof is, imagine if that glass were clear. Imagine how much solar heat you would get if you parked that in the summer. How hot that car would be. So you start up the car, maybe open the windows, turn on the air conditioner to cool it off. Well, the thing is about an electric vehicle, all the power for the air conditioner comes from the same source as the power for the drivetrain. So if you run your air conditioner, you're going to shorten your driving range. So developments like electric vehicles push glass makers to try and do things, to find better ways to control the energy flow in and out of the car. And as you can see, these are some of the big numbers for NSG. On the website it says that about a fifth of the automobiles in the world have NSG glass in them. So, let's talk about some technology here. We'll talk about flat glass manufacturing via the float glass process. We'll talk some about solar cells. We'll talk about the use of transparent conductive oxides in solar cells that use photovoltaics. And then at the end, I'll touch on a few other applications of the TCO materials. So this is the flat glass manufacturing. And we're talking about soda lime glass, which is the glass used in buildings and cars. And flat glass, meaning flat or maybe curved. We're not talking about, I'm not talking about bottle glass or fiberglass. So the process starts, you gotta have some batch material, so it's sand, silica sand. Sand doesn't melt very easily, so soda ash is added to mix with that silica and reduce the melting point. The problem with soda silica ash, or soda silica glass, is that it dissolves in water, slowly, but it dissolves in water. So then you have to add calcium carbonate to add some durability to the glass. Magnesium carbonate's also a good material. Iron oxide, there's always iron oxide in sand. So usually some is added to give a consistent color. And the other thing about iron oxide that I won't go into here is that that is what absorbs the red and the near-infrared light, and that is really critical to how the heat is absorbed in the furnace. So you've got to have some iron oxide in there to melt the glass. And then, of course, for architectural glass and the rear glass of cars, you have other colors in there. So once the glass is, the batch is poured into the furnace, there's an existing melted glass in there, the batch falls on top, and as it progresses down the furnace, I was going to say, is this a pointer? I didn't check about that.
I don't think so.
Let's just see if there's a pointer on here. That's all right. We'll go with this. As the glass flows down here, you can imagine, one, you've got to melt it all. You don't want any of the little clumps that don't melt, because those will show up in your window, right? And then there's bubbles. Sometimes water is sprayed on the batch to keep the dust down, so you're getting the water off. And then some of these materials, like these carbonates, give off CO2. So you've got to get all the bubbles out, and once you get the glass fully mixed, then you've got to get it to the right temperature. And at this point right here, the glass flows over a spout, meaning it flows, this molten glass, it's kind of like molasses or honey, it flows onto a bath of molten tin. So the glass flows and floats on the tin, and it spreads out. And I'll show a picture of that in a minute. So then as you progress down, the glass is formed here into a sheet, formed at the right thickness and the right width. And once again, once you've got the forming right, then you've got to reduce the temperature of the glass to get ready for the next stage, in which the glass ribbon is lifted up on these rollers. And the glass has to be at just the right point that it's solid enough to be supported on the rollers. If it's too solid, it'll be brittle and maybe break. And if it's too warm, it'll sag and maybe drag on this lip or get marked by the rollers. So the glass makers watch this point very carefully. You've got to be within like 10 degrees to get that consistent process. And then it goes down the annealing layer, and you can imagine the outside of the glass is 3 meters wide. The outside of the glass would cool faster than the inside, so you've got this big enclosed annealing layer to keep it cooling uniformly across the width down to the cold end. And then at the bottom end, it's cut into block size. Total length of this glass float line from the furnace to the end is about a quarter mile. So when I was working, we would be working up here and then going down and checking the glass. It was really good exercise. So this is the float glass operation. You can see down here, this bit down here is molten tin, and you can see it's very flat. So if you want to make something flat, pour it on a flat surface. This is the glass right here, and you can see a little change in color, a little change in reflection there. This ribbon's moving about 10 meters a minute, as I said. These are heating elements up here, because you've got to keep the temperature uniform and controlled. And then you can see the reflection of these heating elements in the tin. These are the machines I referred to a minute. They're called top roll machines. You can see it's got a little knurled wheel. And so those grab onto the glass, they pull it out, and keep it going in the right direction. So we'll come back to that a little bit. So flat glass, just some numbers. So the furnace put in about 600 tons of batch a day. The furnace operates 24/7, 24 hours a day, 7 days a week for 10 years or 15 years. Because once you build the furnace and you start heating it up, you can imagine the steel superstructure starts to expand, the bricks and the refractory change size a little bit. So you don't want to do that. So you heat it up once and you keep it there. As I said, the ribbon moves about 400 inches per minute, 10 meters per minute, 3.2 meters wide, cut size. For architectural glass, we might cut 6 meter by 3 meter plates. And then we would ship them to the window manufacturer, who cuts them down to whatever size they need. For automotive glass, you might have a smaller block size here that would then be cut down to the windshield size. So let's talk about photovoltaic cells and modules. So generically speaking, there's two types of solar panels: crystalline silicon and thin film. Crystalline silicon is about 90% of the global market. Thin film is about 10%. So within the crystalline segment, you can see monocrystalline is the highest efficiency, about 24.9%. It's also the highest cost. There's another segment in there called polycrystalline, less efficient, a little less cost. Thin film segment, in terms of large-scale manufacturing, cadmium telluride is the only real contender right now, 19.9% efficient. Once again, a little less, but lower cost than the crystalline silicon. And those are the efficiencies, I'll show this chart on the next page, from the National Renewable Energy Laboratory, which tracks champion module efficiencies and champion cell efficiencies. So, in the thin film segment, there are several other technologies out there. Cadmium, or copper, indium, gallium selenide, pretty good efficiency. They have been made in larger areas, not nearly as many as the cadmium telluride. Perovskite, those are really a newer technology. Small area efficiencies of 18.6, a lot of hope for those. Organic, not as high of efficiency, but there are applications where organic photovoltaics will be able to fill the need maybe better than some of these others. So, the thing is about all these technologies have different glass requirements. I'm going to focus on this segment because this is what I worked on and this is what we make here in the US. I'm not sure that there's any glass made for crystalline silicon cells in the US right now. It all comes out of China and elsewhere. But we'll talk about this. So this is the chart I told you from NREL. I realize you probably can't see all the detail, but it's a really great chart. It goes back to the late 1980s. They've been tracking solar cell performance since then. Every technology, so it's interesting to see that data. So crystalline silicon. I don't know a lot about this, but I wanted to talk about this to motivate why we focused on thin film technology. So if you want to make crystalline silicon solar cells, you got to start with high purity sand, some good silica. Smelt that to get silicon metal. And I'll pause here for a minute. That periodic table up there of all the elements is great. I didn't realize that was here. If I had, I would have taken a photo and put it up there, because there was a little chunk of silicon up there. The initial smelting, there's a lot of impurities. You've got to have really pure silicon, so then the next step is to purify that. Then that pure silicon is put in a big vat and melted. And then you take like an aluminum oxide rod, and put a little crystal of silicon on there. And you stick that into the vat, slowly turn it, and pull it out. And they pull out these big, long crystals of single crystal silicon, meaning that silicon atoms are lined up in planes uniformly over that length, 6 inches, 8 inches, 12 inches in diameter. And that's a process that was developed in the semiconductor industry to make computer chips. So you take that rod of silicon, you slice it, then eventually you want to cover a big area uniformly, right? Cover as much area as possible. So that those round wafers are then, they cut off the edges so you make them like rounded squares, and then you can see that rounded square there, and then you make your cell there, you fabricate your cells together into a module, and you put your modules in the field. So I'll show a cell diagram in a minute. The polycrystalline I won't talk about. It's a similar kind of process. Still have to melt and purify. In that case, you make like a square block instead of trying to grow one single crystal. So then to make your module, you take those squarish cells and you sandwich them between two types of plastic. You have glass on top to provide protection from like hail or rain, of course. And then on the bottom, you can use glass, you could use a metal backing sheet or a high-tech polymer. Anyway, then you laminate all that together, put a good seal around it, and somehow you got to get the electrical connections to those cells outside. All right, before I get to Scott talk about this diagram, has anyone seen this diagram before? This diagram is outside McMaster Hall. There's a little kiosk out there on the ground floor near the parking lot. And I saw that the other day, I thought, that's it, that's what we need. So this shows kind of the basics of a solar cell. You have your silicon wafer right here, and then somehow you create a p-type semiconductor here, meaning you dope it with something like boron that creates an electron deficient area, and then somehow you dope this area with a different dopant, make it electron rich. And the thing about making the n-type semiconductor, the p-type semiconductor, and putting them in intimate contact is they form a voltage. Automatically you get a voltage form. So if you can get an electron somehow in the vicinity of that voltage, it will automatically flow. So that's where the sunlight comes in. There's some electrons in that material that maybe, with a little activation, absorb a photon from the sun, gives that electron enough energy to move. So you've got a voltage, you've got an electron, but of course electrons don't move unless they're in a circuit, so you have to have a back contact, which is easy. Well, relatively easy, because it just has to be a metal that can take the current one way. The front contact, though, is critical, right? You've got to have a circuit, so you've got to have a contact there. In this case, this might be little silver bars, so you can see the trade-off there. You want small bars, so you get as much light through, because those will block the sun from getting to the active area. But on the other hand, you want those bars as thick and as wide as possible to reduce your electrical losses. So right there, you have a key trade-off that that the solar cell manufacturer has to figure out. We're talking about that. So This just shows an array in the field, and I'm talking about making the bulk panels. There's a lot of work that goes into the edge seal. Water can seep in, oxygen can get in. So a lot of work there. And this is really a slide for the chemists in the auditorium here. I had a friend that worked for First Solar in the early days who used to like to say, any physicist can make a diode, but the real skill is protecting it from the weather for 20 years. So you can see in manufacturing crystalline silicon cells, there are some fundamental losses. You make this nice high purity wafer, put a lot of expense into that, then you slice it with this diamond saw, and you lose a lot of material in silicon dust. And then you're going to take those round wafers and make them into squares, so you're going to lose those sides. So you lose in trimming the wafers. And then the wafer thickness, typically you want these wafers to be self-supporting so you can lay them out. But the thickness required to be self-supporting is usually thicker than the amount of material that's actually active in the photovoltaic device. So the concept in the 1970s was, could we reduce the cost by applying a thin coating over one big piece of some low-cost substrate to fully cover it and then avoid all these lost steps out here. And that is the motivation for my research advisors there back in the 80s. That is what motivated his work. So I came up with this concept of a thin film solar cell. I'm sure I can't even tell you right here because that's been the most successful. So we start here. Once again, we have our semiconductor junction right here. So you've got your N-type and your P-type layers there. You've got a back metal contact. You've got a front contact with the same trade-offs as before. In this case, maybe it's a uniform coating, but you want it thin to reduce any light that might be absorbed there, but you want it thick to maximize, to reduce the electrical losses. So once again, you've got a trade-off here, trying to find the right combination of thickness and properties to get what you need. So then the process that was conceived was you take your piece of front glass, and once again there's trade-offs there. You want thin glass so you get as much light transmission as possible, but it's got to be thick enough to support the cell. You want it self-supporting, you want to be able to withstand snow, you want to be able to withstand hail, wind load, all those things. So once again, just choosing the front glass thickness takes some work. So you take your front glass, deposit your transparent conductive oxide, deposit your semiconductors, your metal, and then put a polymer sheet in there and laminate it to a piece of glass or something else in the back. And the back glass has some challenges too, because once again, it can be strong. You don't want it too heavy because somebody or some crane is going to have to lift these up and mount them. If they're on a roof, you don't want it too heavy. But you also need to drill a hole back there to get the power out, to get the wires out. And every time you cut glass or drill it, you create thousands of little microfractures around there. So you don't want those propagating over 20 years in the field. So you've got to make that hole and then sand it or polish it or whatever to make that safe. So here's a cross-section of a cell. So let me just go back one step. So the concept here was piece of glass, put all these layers on there, put another piece of glass on there. You don't have to do anything with those silicon wafers. So here's a cross-section of a device. So here's the glass. This glass is about 3 millimeters thick, so we're only showing the very top of the surface. And then here are the layers. Here's the transparent conductive oxide layer there, the first semiconductor layer, the next semiconductor layer, and I'll be honest, I'm not fully sure what was above this. I'm guessing this is the back metal contact. There may have been some other steps just to prepare this for the electron microscope, but we'll assume that's what it is. And you can see down here, if you look at these, you can see these are like crystals that grow up. So this is like a polycrystalline material, as is the cadmium telluride. You can see that structure in there. And that's what makes for good performance in those devices. The other thing is this highlights that, although I listed like 5 layers, there's more layers that are shown or than talked about because there's a lot of things you need to do to maybe ensure good adhesion or ensure good electrical contact or whatever. Down here you can see this TCO layer. There is a thin tin oxide here, this little dark layer, and then this little white layer, that's silica. And the idea of that layer is the glass has a lot of sodium in it. This little silica layer prevents that sodium from diffusing into the cell during processing or during the lifetime. So there are other things going on there too. And just to show the 1 micron bar here, so this whole thickness is maybe 3 microns. A human hair is about 70 microns. So this is like 5% the thickness of a human hair on a piece of glass. So here are our 2 modules. You can see here's the crystalline one over here. Here's the thin film one over here. You can see conceptually, maybe it's a little easier to manufacture. Maybe. So we got all those layers we want to put down. So the first question is, the first layer is the transparent conductive oxide. What material are we going to use, and how will we deposit it? So we look at our periodic table, and these are all metals here. They all form oxides, or these are transition metals, these are main group metals. They all form oxides. Most of those metal oxides are insulators. They aren't any good for this process. But since the early 1900s, people have identified a few metals that form oxides that can be electrically conductive. So we have zinc, cadmium, indium, and tin, and those are all up in that display up there. But further complication is that tin oxide, if you make it SnO2, it's conductive, but not great. To make it really conductive, you need to dope it with other things. And so these elements are used to dope these elements. So for instance, if you make zinc oxide on its own, it's not a great conductor. But if you dope it with something adjacent to it, calcium, it's a good conductor. Or aluminum, you can make tin oxide with antimony in it, tin oxide with fluorine. You can make indium with tin in it. You can make cadmium with tin in it. So there's only a handful of candidates here, but there's quite a few combinations to look at. So let's look at some of those combinations. One of the best materials is this cadmium tin oxide, cadmium standard. And you see, in the business, everybody has these little 3-letter initials, right? So CTO, very good conductivity. Problem is cadmium is pretty toxic. And this material itself is not. It's stable. So that's okay, but from my point of view, when you see how we make our coatings, any residual cadmium from the precursors that we might use, or maybe in the exhaust system, would be an issue. Indium tin oxide, very good conductivity. This is used all over the place. I'll show you some pictures later. The actual abundance of indium is not great, and the price is volatile. So we looked at that. We ruled it out. Fluorine doped tin oxide. So tin has low toxicity compared to cadmium, and high abundance compared to indium. It's not as good conductivity-wise, but it's pretty good. Tin doped with antimony, similar, but that antimony dopant makes the coating a little, gives a little absorption, a little purple color. So you don't want that in the solar cell. It might be good elsewhere, but not in the solar cell. And then zinc oxide, very good conductivity. And you can dope it with a couple different things. Unfortunately, zinc oxide dissolves in vinegar. So it could be a really good coating on architectural windows. But you got to have a good protective layer on there. So you can see nothing's perfect. So we have some materials to choose from. How are we going to coat the glass? And they kind of go, they interact. You can't just focus on one question or the other. You really have to deal with both. So at the time we were looking at this, there was chemical deposition, a spray process. So you hit up the glass, you spray this chemical on it, a hot glass, the chemical reacts on the glass, makes a coating. Another process, there are vacuum processes. Livio and Sword used to operate an evaporation process, which was pretty amazing. Once again, you have to unload the plates from the float line, cut them, you wash them, put them in a vacuum chamber, which takes time to pump down, and costs a lot of money for those big vacuum pumps. Then you coat your glass, you vent the chamber, move it out. So it seems like kind of a slow process. So somebody came up with the idea, why don't we coat the glass right on the float line, right? So the glass should already be clean. If you coat it right after it's formed, it's clean, or so we thought. You don't need a vacuum chamber, and you can use the temperature of the hot glass to drive the chemistry. So no need to reheat the glass, coat it, and cool it down. Just coat it when it's hot the first time. You can imagine that would seem to be a better energy approach. So here's our float glass process again. So you might remember I said, in here we're forming the glass into a sheet. By the time it gets here, it's in a sheet, and it's a well-defined thickness. So if we look at that tin bath from the top, here's where the glass comes in. I've kind of expanded the length. The glass comes in and pours over this spout, and they said it's like molasses, so it kind of spreads out. These are those knurled machines that help bring it back to a stable, to the right thickness. By the time it gets here, you can see how the bath now narrows down. By the time it's here, it's stable in thickness. It's not going to get any wider or any thicker. But it's still too hot to lift out onto these rollers. So the original purpose of this part of the bath was just to get that formed sheet into a temperature where you could handle it. So that's when the glass scientists of the 80s said, why don't we try to coat it right there? It's flat, it's hot. The problem is the bath is designed for to make glass, not to coat it. So the people that started coating had to figure out, well, how big can we make the coaters, and how many can we put in given the space that we have. So let's go back to our table of candidate materials. You can see we rolled out cadmium due to toxicity. That process I showed you, I'll show you a coater in a minute. You can see that materials can leak out into the atmosphere. We don't want that. Indium, as I said, the price is bad. We ruled out that to absorption, and that dissolves in vinegar. So that brought us to tin oxide, fluorine-doped tin oxide. And that fluorine-doped tin oxide is used in other industries, like for coating glass bottles, for instance, which could be a different talk. So we settled on that. So then the challenge is, can we make 300 nanometers, which is what we needed for sheet resistance, in less than 10 seconds? Because the glass speed is fixed. They're not going to slow down the glass for us to coat it. You got to coat it. Here's your space, here's your time, make it work. So this is an example of a CVD coater, and this is outside the bath, meaning this is on the plant floor after it's been cleaned. When you're ready to coat, you roll this in, this is a trolley system up here, you roll that in and stick it into the bath and lower it down on the glass. So it's hard to see much here because, so this is a beam, that's just a beam to support the coater. There's a beam on the other side. Then there's insulation, because if you put metal beams in that hot bath, they're going to sag, right? So you got to put the metal beams in, and they've got to be water cooled. So those beams are water cooled channels in there. So, and you don't want those water cooled beams to, the problem is they're going to cool the glass. So you've got to insulate those really well so they don't cool the glass. So then the coater is behind that insulation. So you can't really see anything. But I do have a little diagram here that kind of illustrates the concept. So this is the coater cross-section here. And this is deceptive because this is the distance across the ribbon. This is just a cross-section. So this coater goes 3.2 meters that way. And then this is about 20 or 30 inches in the ribbon direction. So the basic idea is you feed gases in. Somehow you make sure they're all well mixed. Flow them onto the glass, and you exhaust out each side. So we might put 500 liters in, 500 liters in there, and exhaust 500 out there and 500 out there. So if you put in 500 and take out 1,000, then the excess gas is going to come from in here. So you're going to suck in gas from the bath atmosphere. So everything goes out. You don't want any of those leaking out anywhere else. So you can see we try to control it with gas flow and pressure, but it's still open to the atmosphere. I mean, the other thing about this coater is that the distance between that coater face and the glass is about 1/4 of an inch. So you've got a ribbon of glass that's 3 millimeters thick. you've got a coater that weighs several tons, and you're trying to lower it down, so it's the same distance above the glass here as it is there, and it's not tilted either way. So that was quite an engineering challenge. I'm not an engineer. So that was quite a challenge to make that work. So the other thing about this process is that it's not a spray process. Think about a spray, like a spray bottle at home, you pull the nozzle and you get little droplets. That was the early way glass was coated, or that was one way it was tried at least. The problem with those little droplets is it's two-phase. You have liquid and a gas. And when that hits the glass, you get like a little mottled pattern. So this chemical vapor deposition means we choose chemicals that are a gas, not a liquid, and we carry them in a gas so that it's just a single phase. So we are able to control the color and the pattern much better. So the end of that story is good news, bad news. You look at this solar cell device, we make the glass, we coat it with tin oxide, but we can't make cadmium or even good quality amorphous silicon by our process. So that's where the solar manufacturer comes in. They make the semiconductors. We can't make good metals either. So that's by a different process. So the bad news, the early concept that motivated this work early on was to deposit low-cost thin-film solar cells on the glass float line. It's probably not going to happen. The good news is that depositing fluorine-doped tin oxide glass on float lines was implemented very successfully and has enabled some other technologies. So this is just the history, and I want to focus on this because the first online coating systems were developed right here in Toledo by my engineering colleagues, and they were developed to supply architectural glass coatings. Right after we did that, we started marketing what we call tech glass, which is a trademark, transparent, electrolyte conductive. And in the early days, I don't remember what year it was, but I can remember taking glass over to when Solar Cells Inc. had their development site here. We used to bring glass over there. So after we had some success, OLF licensed the coating process to NSG. They didn't own us at the time, but NSG learned about the process, they wanted it. Then OLF Pilkington installed it around the world, various places. And as of now, NS3 Group is operating 5 coating plants devoted to the solar industry. Next year, the Rossford plant here, which has 2 float lines, one for automotive glass. One of them will be transitioned to supply for solar. So this coating operation has taken over 10% of the NSG assets. So there are some other applications of this TCO coated glass, the fluorine-doped tin oxide glass. But this is a university, so we need a quiz. Anybody know who these 2 people are? Not you, Nick. Anybody know? Anybody know where these statues, these busts are located? All right. Well, this is, of course, Harold and Helen McMaster, and they are located on the ground floor of McMaster Hall. And Harold McMaster did a lot. So, in the 40s, Harold McMaster was a physicist and an inventor at Libby Owens Ford. And he came up with this coating on glass. This is at a time when aircraft were starting to fly high enough that they needed pressurized cabins, and that the glass could develop ice from the cold temperature. So he did this work, filed the patent in 1942. It was not published until after World War II. And it was a process for making antimony-doped tin oxide by chemical spray on aircraft windshield. So he left LOF. He started 2 companies. I don't remember the name of the first one, but the second one is called Glass Tech. They're still around. He sold that company for a cool $100 million. Very successful company. And with that money, he did a few things. Obviously donated some to the University of Toledo. He invested in 2 thin-film solar companies. The first one, Glass Tech Solar, made amorphous silicon, similar to the material I worked on in graduate school. Didn't succeed. The next one, Solar Cells Inc., became very successful. That's the origins of First Solar. So, modern aircraft still use TCO coatings on their windshields. This is an older photograph, but you can see the colored reflection here. It's kind of like oil on water. you get that colored reflection because the thin layer and the thick layer, you get a reflection from the top interface, the bottom interface, and depending on the thickness, those two reflections interfere constructively to give a color. So the blue color is a different thickness of coating than the red color. Now that doesn't matter in transmission to the pilots because the amount of light reflected from the inside is a lot less than the amount coming through the window. So they don't see it. It doesn't affect their vision. And that glass is not made by us. That's not our product. That is typically a different TCO material, indium tin oxide, deposited by a different process. This is a classic, an old diagram that shows basic construction of an aircraft windshield. Glass, polymer, interlayered glass. And that's actually the same as an automotive windshield. We have two pieces of glass and a piece of plastic. And that plastic serves a couple functions. Number one, if you impact it, if your head impacts it and the glass cracks, it sticks to the plastic. And also it keeps the occupants in the vehicle, right? You don't get ejected. And conversely, if something impacts from the outside, it might crack the glass, but the glass shards won't go flying, they'll stick to that plastic. But what I liked about this diagram is that it has this NESA anti-ice heating system. That is a tin oxide coating. That was the trademark of one of our competitors 30 years ago. It stands for non-electrostatic coating. So it's a coating to provide a little heat to that outer ply to keep ice from forming on it. Refrigerated display cases. You probably don't notice those like I do. But I was in a convenience store and I found this case. And I took this photo because the lighting was just right. If you look at that, because I wanted to get a photo of that upper left corner. If you look up there, you'll see a silver bar across there. That's because this glass has a tin oxide coating on it. And our customer takes that glass and they apply this silver bus bar, and then they heat it up, fire it, make it hard. And then each of these little refrigerator doors has a little power system. So once again, you can run current through there, heat that glass so that when somebody opens it, looks inside, and the humid air gets in, the humid air doesn't condense on that surface. Electrochromic glass. These electrochromic automotive mirrors have been around a long time. We were supplying glass to one of these companies when I first started. And the basic idea of electrochromic glass is you apply a voltage to the glass and it changes color. So how does that work? So here's some samples. On the right are two pieces of glass laid together like that with a coating in between them. And I show this little diagram here. I'm not sure if it helps or not, but you can see here's a front piece of glass with a coating, and there's a little silver contact there. Here's the back piece of glass. You can see they're offset. So that's what we're doing here. This alligator clip is connected to this glass. This alligator clip is connected to this glass. And then there are those magical coatings in there that when you apply a voltage, the coating turns blue. So, as I said, these were available as early as 1989, small area. It was about 2000 that a company called Sage Glass started up and started trying to make architectural size windows. And two of the key people at Sage were people that I worked with, left my company to go there. So we had an opening. They needed a project manager because we had an electrochromic project. I said, yeah, I'll do that. So I applied, I got the job. But within a year and a half, we stopped the project. We just could not do it. We could make beautiful little laminates like this that would turn blue. But when we went to 12-inch squares, they did not look so good because such a sensitive material that, I can remember one time we powdered up our laminate and there was a beautiful fingerprint right there. It's like you didn't see it there, but when you do it there, and a little bit of sodium in the oil in your finger changed the color of that. So we stopped the project. But then a few years later, this company, Toledo, came along. They had a really good technology, so it seemed to me, and they changed their name to View, which is a little more memorable. They've had over $1.5 billion invested in them. I'm not sure they're going to succeed, but they have a very expensive process and some really great installations. And I'll show you a couple of those. These are both Sage and U. Oh, but first, how do electrochromic windows work? That's the question. Once again, you have a piece of glass with a transparent conductor here, tin oxide, another piece of glass with a transparent conductor, and then on this side you have this electrochromic material, and this ion storage material, and some sort of polymer or ionic conductor in between. So this material could be like nickel oxide with a little lithium in it, and this material could be tungsten, is always tungsten oxide, I should say. And when you flip the switch from off to on, these lithium ions move from here through there and form this blue tungsten oxide. And at the same time, then of course you get electrons flowing in the outer circuit. So this material, this material is pretty amazing. It allows ions to move through it, but it doesn't conduct electricity. So anyway, you can turn your glass from clear to blue. So here's some examples. This is a restaurant. You can see it's on a lake or something. And in the morning, it's really a nice view out there. But in the afternoon, when the evening sun's coming through, you can see how much glare you get through those windows, through those top windows. So sitting here might not be very comfortable. And of course, you could put blinds on there, but you wouldn't be able to see out. So these are electrochromic windows that darken in the evening. Same product. Over here, you can see they switched on half of the windows, and you can see you can choose different colors. So this is dark blue, this is light blue. And you can see how uncomfortable this room would be in full daylight. So here's an office. This is a good example too. Great view up here. But can you imagine trying to work at this computer in that glare? So it helps with glare, but you still maintain a view, because if you had blinds, you would lose that view. In view, there's a couple ways to control it. You can put a controller on each window. They also make these integrated office control systems that controls everything centrally, based on the position of the sun, the time of day, etc. So View has done a lot of work. They identified airports as a major important market for them. So here's the Charlotte airport. They built some new terminals a few years ago. And you can see this side the windows are clear. This side the sun's moving towards that side, so they darken those so you wouldn't get so much glare in there. And for the purposes of this photo, they put the CLT, their initials, in the window there. But you also see electrochromic windows in aircraft. Not too commonly. This was a window made by a competitor of LeBeau's Ford, PPG. And this is in the Boeing 787 by Air Nippon. And you can see, once again, when you're in the airplane, there's a lot of glare. You pull the shade to stop the glare, you can't see out. But with this window, you can reduce the glare, but you can still see out. And you can also see some variation in color here. I don't know what's going on there. Okay, last application, displays. So these are what I call small displays. We've got iPhones here. We've got a laptop, we've got a desktop, and this is 72-inch display, but it's small. Because this is a large display. This is like a 3 or 4-story facade, and this is an LED display that you can change, that you can animate, that can move. So how do these work? There's a lot of different display technologies. Here's another example. You can see in this building they're choosing to run an ad, but you can see it's also transparent. So if you're in the building during the day, you can still see out, but at night, they can flip on and run their ad. So the basic concept here is you take a piece of TCO-coated glass, tech glass for this application, take that and you pattern the coating, like you laser scribe every half inch or whatever. So you create isolated lines. And then you take another piece of glass and scribe it, but lay it like that, so that at the intersection of those, at every one of those intersections, you put a little LED, a little light emitting diode. So then you can have a big display, a big array, and your computer then figures out which lines to charge at what time to make your image. So most of these are all, as I said, small. Those are all indium tin oxide, sputtered on a special kind of glass, not on soda wine glass. But you can't make that glass in this size. You can't make borosilicate glass in that size cost effectively. You can't make indium tinoxide in that size cost effectively. So if you want to make really building size displays, you got to use something like fluorine tinoxide. So, thank you for your time and attention. I'm happy to try to answer a few questions. That's a good question. I don't think those get that high. I don't know if anybody else can answer that, but I mean, there are a few energy losses. Some of the light does go into heat. There's the thermodynamic limit, meaning that if you have a body at a certain temperature and a body at a cooler temperature, you can get heat transfer. But what we learned from 19th century thermodynamics is that the maximum there is about 40-some%. You can only get 40% of that energy to other source. So they do heat up though.
The gas,
I recognize it.
the gas furnace is a gas.
Yes.
In the forming section, it has those heating elements that look like the little.
Right.
Why are we using heating elements in there got gas?
Those are electric heating elements. I mean,
Is it better control? Or?
probably. Yeah, right.
So the sphere of Las Vegas, that must be similar to your last picture then, the advertising?
The sphere in Las Vegas. Oh, probably.
That must be your heaven to see that.
Yeah, surprised I didn't find that. I was searching the internet for good examples. Yeah. Anyone else?
Where are we headed with the technology? Is there anything that's going to come up fairly soon that is really going to advance us to the point that it makes it more practical to use solar energy? Maybe what are our hindrances that we're
Yeah, I think there's a couple things to comment on that. First of all, there are people working on a lot of different things, and I mean, I've seen a lot of incremental improvements over the years. So that's what I foresee, more incremental improvements. The next thing is that, so the solar cells I showed are all single junction. You have a N-type and a P-type semiconductor, and you absorb that energy. A lot of work is going on in terms of making dual junction, like you make one kind of cell here that maybe absorbs visible light, and a different cell up here that absorbs infrared. So you get more of that, more useful of the solar spectrum. And to go back to your question, imagine you've got a solar cell and you're absorbing, for each photon you get in, you get an electron out. So a red photon has a low amount of energy, a blue photon has a lot. They both produce one electron. So that blue photon gets absorbed versus one electron, the rest of it goes to heat. So if you can make a tandem junction, dual junction, you can optimize the absorption, get two different absorption spectra to make better use of that energy. And the other thing is, there are a lot of different segments in the solar cell market. I focused on the solar array, right? So in that case, the 19% efficiency is good. But if you putting solar panels on a roof, maybe in Japan, where you've got limited space, then you need higher efficiency modules, right? And if you're going into space, you need something different. And if you're doing something else, maybe the OLED 14% efficient are fine, or the organic are fine. So that's part of it too, is finding the right solar technology for the specific application.
What's the lifespan these days of solar collectors? You have that, the key is keeping it.
Right. It's at least 20 years. But I'm not sure what they're warranting now, if they're targeting 25 or 30. Certainly there are DOE programs, Department of Energy programs, looking at how can we make modules that last 50 years.
I know that they're working on leaks to emulate.
Yeah, I've seen those.
Wouldn't a solar artificial tree thing be more efficient than these flat panels?
I don't think so. I don't think photosynthesis is very efficient, actually. And to me, I mean, you want to get collect a large area. I've never understood the leaf approach because it doesn't seem to me that's as an effective way to cover a large area.
So this is a question for students or for people just graduated. You have a long career. What did you find was your number one asset, number one attitude throughout all that brought you to learning as much as you have and at one point being
I don't remember your name, but I'm going to...
no.
Matt. So he works in the group that I used to work in. I think there's a few things. Technically, you got to be curious and read a lot. And there's a lot of stuff that I read more than once because I just didn't really get it the first time. Like I didn't understand p-n junctions for a long time. I think, I can speak to my company, LOF, NSG, Pilkington. A lot of the best work we did was when we were a team. If you just focus on what you need to do or what your responsibility is, one, other people can often have advice that'll help you. If you work with other people, you learn a lot. So I think that kind of being able to work together, not being able to accept your mistakes and your ignorance compared to some others. Personal skills. Yeah.
All of your changing color technology is direct current?
Is what?
Direct current?
Direct current, yeah.
Solar cell convert it to alternating current in the house, and then convert back to direct current using on my unit.
Right. There are people at NREL that have made devices which have the solar cell and the electrochromic so that you can just...
Well, I put one of these on the roof of my car, or my Tesla.
There are electrochromic windows, roof lights, yeah, like, maybe Mercedes, I can't remember who's done it. They've happened.
All right, I got the last question.
Oh, good.
So, when you set these production lines, once you get them started, they keep going for,
15 years.
yeah, so you've seen a few of these.
Yes.
All right. So if you want to actually do anything different, like put in, your CBD coders, how much lead time do you have to start working on that to make sure it gets in the next generation of the parts?
Right. That is the challenge. My mind went a little different spot. So I built a furnace. The one we built most recently was, like $180 million glass lamp. So when your company is looking at investing that kind of money, you've got a choice. Well, we could copy that one because it worked for so long. But our customers are telling us there's this new technology for, gas burners or something. Maybe we should put in those because they'll be better and more efficient. But if we put those in, they better last 15 years. So you've got some big risks there, right? And so to your point, Nick, normally, until we built a plant in Lucky, Ohio, so we built a plant in Lucky, Ohio, commissioned that a couple years ago. Until that point, every glass coating operation was based on, well, this plant has this amount of space, what can we fit in there? So with the Lucky plant, we were able to step back and say, okay, this is the product we need to make. Ideally, we'd have this many coaters. This is how we're going to design the length of the bath, the size of the furnace, the whole bit. And that planning process was probably a year and a half. And then acquiring some of the, like once you decide you're going to do a coating plant, then you order the materials and have somebody fabricate the coaters. That's a year-long process. And so it's like at least 2.5 years.
So you don't modify the existing line, put the coater in?
That's what we did for the first 30 years of my career. We finally had the opportunity.
So you have build the plumbing well in the slide.
Yeah, that's right. Hey, is there anybody from First Solar here? All right. One of the key differences between our company, so we supply First Solar glass, every one of our coating plants is different. The First Solar philosophy was copy smart, right? They built one line, they built 3 more, so that's one set. Then the next plant, they copied those and built those. And so if they introduce an improvement, it goes everywhere. Whereas everything we do, every time it's a little different. Because, as my one boss said, MSG moves at glacial speed. Right. Gary.
So, all that burning of natural gas, is making an awful lot of CO2, but
Yep.
also some of the ingredients you mentioned, the lime and so on.
Right.
Can you tell us how the gas industry is approaching CO2 and trying to get those numbers down?
I wish I could. I will tell you this, that 10 years ago or so, maybe longer, one of my colleagues and I did an analysis. We did the energy payback analysis. And we determined that for the energy used to make our glass, it's like a year and a half. So we make the glass, sell it to a company like First Solar, it's making 16% efficient modules at that time. That energy is paid back in 16 years, in a year and a half. So over a 20-year lifetime, it's definitely a net benefit. And we looked at CO2 as well. And I don't remember what we came out with that. Pilkington, if you go to the MSG website, there is a segment of the group that's working on sustainability. And so, for instance, one thing they did, they tried firing a furnace with hydrogen in the UK. And that was funded by the UK government. You know, they supported a company that was developing ways to produce hydrogen. And then they had different companies lined up to use that hydrogen to see how it worked. So we've tried firing a furnace with hydrogen. Yeah, I don't know, that's a good question.
Is there a regional solar cell? In other words, Ohio is kind of cloudy 50% of the time versus Las Vegas. Is there any advantage to making a shade area
Yeah.
solar cell?
Well, so the different technologies have different features. And Nick, jump in here if I say anything wrong. Like crystalline silicon is the most efficient. But when they heat up, the efficiency goes down. Cadmium telluride has advantages in that it doesn't degrade as much when the temperature goes up, and they do a better job of collecting, converting energy that's off angle rather than direct. So there are subtle differences, for sure. And that's the kind of decision maybe the power company would make, right? If a power company says, we want to build, 500 megawatt plant to meet this requirement for renewable energy, then they would be working with, First Solar and other companies who would say, we can do it for this, and this is the characteristics of our system. So they would probably make that.
And is there any other source of light that can be used besides the sun? In other words, we light up the streets at night,
Yeah,
and we suck some of that.
good question. I mean, another technology that people are working on are bifacial solar cells. So you can see you get most of the light, but there will be some light. Look at one of those roads, there will be some light reflected from the back on the ground. So if you make it bifacial, then you can get the direct light as well as what's reflected back.
Okay, so it's a couple minutes after 11, so in the interest of time, let's thank Dr. Strickler one more time. If there are more questions, I'm sure he's happy to chat a little bit